Okay guys, I'm gonna try to show you this. We're gonna talk today about ocean currents. So basically these are gonna be surface currents in the ocean. All right, and the reason we're gonna talk about these now is because the winds, the prevailing winds that we talked about last time are going to create these currents. So if you remember last time in the quiz that I gave you about prevailing winds, I basically put a question in there. It was an all of the above question that said, how do we know wind carries energy? If something can push something down, it's imparting energy into it. So if something is moving, it has kinetic energy. So the fact that wind is air particles that are moving, that means that they have kinetic energy, and then we can impart that kinetic energy into other things and basically convert that energy from one form to another. So in this case, when we are blowing wind onto the water in the ocean, obviously we're going to create waves and things like that. We'll talk a little bit about waves later. But what we really want to talk about is as it pushes that water, if you just keep pushing it, it's kind of like the fluid air that we were talking about. So if you remove particles from a location, other particles want to fill in, right? And so if we continue pushing and moving particles, then other particles filling in, and we push those and fill in and push those and fill in, and we end up with essentially a conveyor belt where we just continue pushing those along as long as the wind is blowing. So if you recall from last time, we had winds. Equators here. Remember the equator is 0 degrees latitude. Remember up somewhere around 30, we had wind basically doing this, right? And notice I repeat Asia over there because I want you to be able to see the entire thing. So this isn't some sort of weird new map. This is just our normal map. And then down here, remember, wind is doing this, and these are our trade winds, right? And so then at the 30 to 60 and 30 to 60, you have westerlies, remember? And again, this is all crayon drawing pictures, and then 0 to 30 down here, you have westerlies again, all right? So, and then if we want to look at the poles, which we're not going to look at those as much, it goes back this way, right? And then these guys go this way, right? So if we look at that, these are our winds, our prevailing winds, right? And so if we are pushing water from here, let me change colors. From here, if the wind is blowing, and the wind is blowing all across here, not just where the arrows are. So if we start at land and we blow wind across here, we're gonna push water towards the equator here. Now remember, fluids will turn right from their intended projected path in the northern hemisphere due to the Coriolis effect. So when we factor in Coriolis, this is actually going to turn right even more, right? So as we are pushing this water this way, it's wanting to turn right. And really, if we are, turning right and turning right and turning right, then eventually we will get back to a point where the wind is pushing the water this way due to prevailing winds. And that will want to go right and right and right. And if we continue going right and right and right, we end up with this circular rotation of water, okay? If we do that in all of the oceans, so find land, we're coming this way, right? And if we keep turning right, we'll end up coming this way. Then if we do that down here, we're turning this way, and then eventually we're turning this way. Here we're turning this way. Eventually we would be turning back that way. And then in the South Atlantic, we're turning this way, and eventually we would turn back that way, right? If we do that, then this is going to be our ocean surface currents. So if I delete all of this real quick, I want to actually make it, well, let me start here and then we'll come back. So if we look again, equator is right here, right? So I'm going to switch to my red color, and we'll clean this up in a minute, but I'm going to switch to my red color. That means that all of this right here is warm water, because it's right here near the equator. It's going to be getting warmed by the sun, and then the wind is going to be pushing it on up, right? As it approaches up here, right, towards the poles, this water is going to start to cool down, and it will start to circulate this way, right, because we're turning right, turning right, okay? So we've got warm water here, we've got cold water there. Now let's apply that everywhere on here. So I'm going to erase all of this and we're going to redraw. So I'll start with my warm water. In the Pacific Ocean, our warm water currents, still on erase. Our warm water currents are basically going to start here, cycle up this way, and these are surface currents, remember. So they go that way, right? Then in the North Atlantic, same thing. They go that way, right? Then down here in the Indian Ocean, they're actually going to go this way. And then here in the Pacific Ocean, they will go this way. And then in the South Atlantic, they will go this way, right? Then if we come back in and we add the cold water side of that, remember up here near the poles, it will cool and come down. Right? And then over here, it cools and it comes down. And then over here, it cools and comes up. Here it cools and comes up. Here it cools and comes up. Now, don't get these confused with convection cells. These are not convection cells. This is surface current water being pushed by the wind. The only reason this is warm is because it's near the equator. So as it gets pushed up this way, now it starts going further north and it starts to cool off, and the winds are still pushing it. Remember, those westerlies are pushing the water this way now. And then if we keep turning right because of Coriolis, those colder waters will come down this side because there's nowhere else for the water to go because of land, right? It starts to push it down. So we have cold water currents here. So we'll just say this is cold water. This is warm water. Hopefully your red color coding worked there. These are surface currents, right? Surface currents, meaning that they are only at the surface of the ocean. They are not deep water currents, right? And these surface currents that do this big circular flow have a special name. They are called gyres, right? So this is the North Pacific gyre. This is the South Pacific gyre. This is the Indian Ocean gyre. This is the North Atlantic gyre. This is the South Atlantic gyre. So on our globe, we have 1, 2, 3, 4, 5 gyres, which are these really big circulating surface currents that are driven by the wind. They are also warm water, cold water currents because they are driven by the wind from the equators toward the poles, and then the water from the poles comes back towards the equator. Since they're at the surface, they're allowed to cool when they get up here. They're allowed to warm when they get here. So it's basically just these circular currents. Now notice, in the northern hemisphere, gyres rotate clockwise. In the northern hemisphere. In the southern hemisphere, gyres rotate counterclockwise. counterclockwise in the southern hemisphere, right? If we know those things, we're pretty good. That's surface currents, okay? Now, if we think about this, if anyone has ever been over on the West Coast, the water there is typically what? Cold, right? If you've ever been on the East Coast, the water there is typically what? Warm. Now, all of this is surface currents on, you know, kind of that laminar versus turbulent thing. Nice and pretty, that's how it works, right? But we have other things at play. Number one, we have the Tropic of Cancer. Number two, we have the Tropic of Capricorn. So that is going to alter things sometimes because in the summertime, this will all rotate down. So these current warmness and coldness will be a little bit different. And the wind patterns will be slightly different. So these gyres actually can kind of compress a little bit, right? And they can also kind of oscillate from the northern hemisphere. They might dig down south a little bit, right? Now what this also shows us is if we're in a boat, right? If you were in a boat right here, you could travel down through this current, and if this were to oscillate a little bit north for you, you could get into this current, right? And then if we took that current, there's also one that we're not talking about, but it's a polar circumferential gyre or something that basically you could get into that, and it could take you all the way around there, come back out over here. You could get into the Indian Ocean, and then all throughout these little bays, there's little different surface current nuances that happen. But ultimately, if you notice, we can get anywhere that we want to go. Get stuck there, but man, you could come around this way, and then this could go out that way, which is back over here, and get out and through here, go back up through here. So you'll actually see, it's a thing called flotsam, which is basically a branch of science that deals with charting ocean currents. And what they do is they actually use cargo ships. Cargo ships typically leave Japan. They're typically headed for the mainland US, right? And a lot of times what happens is somewhere in here they hit storms. And when they hit storms, a lot of times cargo ships can go, or cargo holds can go overboard, or they might even jettison them so that they don't sink the ship, right? So there's actually stories, the first story where this occurred was a bunch of bath toys. And so a bunch of bath toys went overboard right here. And then slowly but surely, those bath toys float like little rubber duckies and whatnot, right? And slowly but surely, they started ending up here, 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 here. They would find them here, here, here. Found them all the way down here. They found them over here, They found some way over here. They found some up here just several years later. So it basically shows that all of the oceans are connected, right? And these currents can move things throughout the ocean. So the currents are really important, right? Then the other thing that's really important is, remember, the only way for oxygen to get into the water is through the surface. So a lot of these surface currents will pick up oxygen from the air and help downmix those into the ocean water column. So the best place for oxygen to be absorbed is in these cold water areas, right? Because warm doesn't absorb it as well. So in these cold water areas, typically you will find more abundant nutrients because there's more O2 there. So if you ever go to the tropics, the reason the water is so clear is because there's not a lot of stuff to help organisms survive and reproduce very well there. So the water ends up actually being pretty clear. If you go to these colder water regions, typically the water is not as clear. If you've ever been to the coast over here on the West Coast, typically the water is not as clear looking as it is on most parts in the warmer Caribbean areas. But all that's just interesting stuff. Main thing you need to know, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. They're called gyres, and they basically go throughout the entire world's oceans, but they're these big kind of whirlpools of circulating surface currents. And they'll take warm water north in the southern hemisphere, cold water, there's water south in the northern hemisphere, and in the southern hemisphere, take warm water south, cold water north. If you've got that, you're good. I'm going to erase that and show you something else real quick. The other thing that can happen in these gyres, and it doesn't matter if this is warm water or cold water, but if this is circulating, you end up with this thing called rotational inertia that actually will start pulling things towards the center. It's a whirlpool, right? You've seen this. You go to like the museums and they have the big penny well where you drop the penny in, the penny spins around it and then goes towards the center and falls down the hole. That's what happens here, okay? There are actually measurements that have been made where the ocean is 4 feet higher over here than it is right dab in the middle, right? Which it may not be 4 feet, I just threw that out there. But basically you have a depression towards the middle because this swirling amount of water, it pushes water out, sinks water in just like a whirlpool would. So what happens is if you have any bit of trash, that trash will slowly circle its way and spiral to the middle. Now, remember I said this isn't perfect, it's kind of squished and it does different things. So what you end up seeing out in the middle of the ocean, where's the pin working? Oh, because it's already erased. What you see is out in here, you get an accumulation of trash. And this is called the Great Pacific Ocean Garbage Patch. They've talked about in areas out off of Hawaii, so right in here, there's actually a huge area that is bigger than Texas, right? So out in here, there's a huge area that's just all debris that's littered in the ocean. I mean, you can find all sorts of stuff. And most of that trash has actually come from the United States and then also from the Asian countries. So you'll get out here and you'll actually find North American trash and Asian trash for the most part out in this area. Then there's another portion of the patch that's kind of on this side. Same thing, you get North American trash, Asian trash. Usually the trash that you see in here, the Asian trash travels this way and then is deposited, and the North American trash goes straight there, right? So you'll see more North American trash here usually. And then also here as well, because the Asian trash takes longer to get there usually. Now, the cool thing about this too is if you remember the great tsunami that happened in Japan in, what was that, 2011, something like that? Actually, sorry, here. That actually caused debris that got washed back out to sea. A couple years later started washing up on the coast of Washington. In fact, entire houses were washing up on the coast in Washington, and then all along the coast, obviously through here too. But basically what happened was lots of organisms at sea see that as a reef, and it actually brings organisms across the ocean as well. So now you have species that typically didn't live in this area of the ocean have now transgressed across there because they have been able to ride these kind of mobile reefs throughout. So now there's a whole process of people trying to study that aspect of how these new species could affect that. They're called invasive species if they're a bad thing. If they're a good thing, then they typically don't call them that. But so lots of things that can happen on currents. Last thing on these currents that I want to show you is when we start interacting with land. So this big gyre goes right through here, right? Now, just like in our Hadley cells, that is going to cause some of these other areas to do different things. So if I'm pulling the water this way, when that diverges away, sometimes you'll end up with currents that go against the flow basically, or go backwards. So you'll get these currents will kind of do that. So in the Gulf of Mexico, for example, this does that. As you're coming across here, that creates a low pressure situation right in here, which then will draw water back out of the Gulf of Mexico. So usually it comes in this way, goes out that way. So all these little areas are usually established by these, and it's not the perfect picture of just this great little surface current. Last thing that we need to know is, in terms of surface currents, we need to get to deep water currents. So let's talk about deep ocean currents, and we're going to be pretty quick on this. This has to do with the equator again, right? So the equator, water warms and gets saltier. Why does it get saltier? Because you're evaporating the water. So you're leaving behind the salt. If it gets saltier, that gets more dense. So the density will increase. If the density increases, that means this water will typically start to sink. So near the equator, you get sinking, warm, salty water, right? So that happens typically at the equator. Then in the poles, as that cold water is coming, that water gets cold. Whoops, that's not cold, that's gold. So the water up here gets cold, and what does water do when it gets cold? It starts to sink as well. So cold equals denser equals sink as well. So water wants to sink up here. It also wants to sink here. So if you got water sinking here and sinking there, then you also have to have somewhere for it to come up. So basically, as this water here is getting saltier and sinking, it's basically pushing water that wants to come up over here, which then will get colder and sink, and then it will want to come back up here. So you end up with this kind of sinking, rising, sinking, rising, sinking, rising. Out off of here, you get this pretty big area of water that is called an upwelling, which is cold, nutrient rich water. And that is all based on densities of water at different degrees and whatnot. The main thing is you need to understand that an upwelling is cold, nutrient rich. That says RIC, so nutrient rich water, right? And that typically happens off the coast of California. And then there's other places throughout the globe that happen as well. There's one that typically happens over here. But usually that nutrient rich, it's colder water, so as it comes up, it's bringing things from the bottom that are dead and start to get recycled. And then it's also, because it's cold and coming up towards the surface, it mixes with oxygen again, which allows a lot of that dead stuff to break down. So you end up with these very nutrient rich areas, which then lend themselves to being good for fishing and whatnot. So deep water currents are driven, let's do this. Deep water currents are driven by density differences, which can come from temp and salinity, which is just saltiness, right? Then surface currents, 2 R's in there, are driven by the wind, right? So if we know that, I think we'll be pretty good. I think I'll stop there for now, and